How does one begin to describe a shape that cannot be seen, a form that exists only as the solution to a set of polynomial equations? The sphere, defined by x squared plus y squared plus z squared equals 1, is familiar enough. We can hold its likeness in our hands, intuit its symmetries, and map its surface. But what of the shape defined by the sum of the squares of 10 variables equaling 1, a 9-dimensional sphere residing in a 10-dimensional space? Or the impossibly intricate surfaces carved out by equations of higher degree, with variables whose values are drawn from the complex numbers or even more exotic fields? Here, in these ethereal realms, our physical intuition becomes a treacherous guide. The language of sight and touch fails, and we are left with the austere, yet profoundly beautiful, language of algebra. This is the world of algebraic geometry, a discipline dedicated to deciphering the geometric content of pure algebra. To navigate this landscape requires a unique kind of vision, an ability to perceive structure within abstraction. And among the master architects of this world, few have built more fundamental and elegant tools for its exploration than Hélène Esnault. Her work provides much of the foundational grammar that mathematicians now use to speak about the deep structure of these abstract objects, forging connections across disparate fields of thought with breathtaking originality. The intellectual environment of the early 1980s, when Esnault began her seminal collaborations, was one of immense theoretical power and lingering classical questions. The work of Alexander Grothendieck had revolutionized algebraic geometry, reframing it in the language of schemes and categories, creating a framework of such generality that it could treat problems in number theory and geometry with the same set of tools. Yet, this powerful abstraction sometimes created a gulf between the new machinery and the concrete geometric questions that had motivated the subject for centuries. A key challenge was to build robust bridges between the world of complex analytic geometry, where tools from calculus and topology were potent, and the more general algebraic setting, which encompassed arithmetic fields like those of prime characteristic. In the domain of complex geometry, a cornerstone result was the Kodaira vanishing theorem. This theorem is in essence a guarantee of simplicity. It tells mathematicians that for certain well-behaved geometric spaces or manifolds, specific measures of complexity, known as cohomology groups, are equal to 0. The vanishing of a cohomology group is profoundly useful. It asserts the absence of certain kinds of geometric or algebraic obstructions, making it possible to construct functions or sections of bundles with desired properties. It is a prerequisite for countless results, from classification problems to the proof of the existence of embeddings into projective space. Kodaira's original proof, however, was deeply analytic. It relied on Hodge theory and the properties of differential operators, like the Laplacian, techniques intrinsically tied to the smooth, continuous nature of the complex numbers. This presented a formidable problem. How could one achieve similar results for algebraic varieties defined over fields of positive characteristic, the finite number systems essential to modern number theory and cryptography? An algebraic proof, one that relied only on the structural properties of the defining equations, was desperately needed. Such a result would unify the theory, providing a single powerful tool applicable across the arithmetic and geometric spectra. This was the intellectual crucible in which one of the most important results of late 20th century algebraic geometry was forged. In a landmark series of papers with her collaborator Eckhard Vierweg, Esnault constructed precisely such a tool. The Esnault-Vierweg theorem on the vanishing of cohomology is a sweeping generalization and powerful analog of Kodaira's result, but proven with entirely different and more widely applicable methods. The innovation of their approach was manifold, but at its heart was a brilliant use of coverings and degeneration. They developed a sophisticated technique for relating a problem in characteristic 0, the familiar setting of the complex numbers, to an analogous problem in positive characteristic. This method, sometimes described as a proof by reduction to characteristic P, was a conceptual masterstroke. It allowed them to leverage the unique structure of the Frobenius morphism, an operation that exists only in the finite field setting, to deduce powerful consequences back in the original characteristic 0 world. They showed how to take an algebraic variety and its associated line bundle, a kind of geometric data package, and use it to construct a branched covering space. By carefully analyzing how cohomology behaves under this covering map, they could translate positivity conditions on the original bundle into the vanishing of the very cohomology groups they sought to control. The theorem itself provides an explicit algebraic criterion for this vanishing. It states, in conceptual terms, that for a projective variety and a given line bundle, if the bundle is sufficiently positive in a precise technical sense related to its degree and the geometry of the variety, then its higher cohomology groups, denoted H sub I for I greater than 0, will all be 0. This result immediately became an indispensable instrument in the algebraic geometer's toolkit. Its proof was a tour de force of modern technique, weaving together ideas from commutative algebra, sheaf theory, and the intricate geometry of singularities. The impact was both immediate and enduring. The Esnault-Vieweg theorem provided a unified framework that subsumed many previous partial results and opened new avenues of attack on long-standing problems. Today, it is a foundational pillar of the subject, taught in every graduate course on algebraic geometry. Researchers use it as a daily workhorse to perform the fundamental calculations necessary before tackling more advanced questions, such as those in the minimal model program, which seeks to classify all higher-dimensional algebraic varieties. The theorem's power lies in its generality and its purely algebraic nature, making it a truly universal statement about the hidden structure of polynomial equations. Having helped to establish such a fundamental tool for understanding the static properties of these abstract shapes, the next frontier involved probing their internal connectivity and symmetries, the very soul of their topology. This inquiry would lead into the equally deep and mysterious theory of fundamental groups and their representations. The profound architecture of algebraic geometry, as revealed by tools like the Esnault-Vieweg vanishing theorem, provides a blueprint of a variety's static structure. It tells us about the global properties of functions and forms that can live on these abstract spaces. Yet, a space is more than its static framework. It possesses a dynamic soul, an inner life of connectivity, captured by the field of topology. To truly understand a geometric object, one must understand how it is connected to itself, the ways one can trace paths upon its surface and return to the origin. This inquiry into the very essence of shape leads directly to one of the most powerful invariants in all of mathematics, the fundamental group. For any topological space, its fundamental group, often denoted P sub 1, is an algebraic codification of all the loops one can draw on it, providing a precise measure of its holes and handles. A sphere, having no holes, has a trivial fundamental group. Any loop can be shrunk to a point. A donut, or torus, with its single hole, has a fundamental group generated by two distinct loops, one passing through the hole and one encircling it. For the complex, multidimensional landscapes of algebraic varieties, this topological invariant has an even deeper, more mysterious algebraic cousin known as the algebraic fundamental group. This object, woven from the very fabric of the variety's defining equations, was for decades a source of both immense fascination and profound frustration for geometers. It promised a gateway to the deepest symmetries of the space, yet it remained stubbornly opaque, its structure almost entirely inaccessible through direct computation. The key that promised to unlock this algebraic enigma was a grand unifying vision proposed in the early 1990s by Carlos Simpson. Simpson's conjecture posited a radical equivalence, a kind of mathematical Rosetta Stone, translating between two entirely different worlds. On one side lay the world of analysis and topology, the representations of the fundamental group. A representation is a mapping that assigns to each loop in the fundamental group a matrix, effectively translating the topological information of paths into the language of linear algebra and transformations. These representations capture the continuous flexible nature of the variety as a geometric space. On the other side of the conjecture lay a world of pure algebra, the realm of Higgs bundles. A Higgs bundle, an object of formidable abstraction, consists of a vector bundle, a family of vector spaces smoothly parameterized by the points of the variety, equipped with an additional piece of data called a Higgs field. This field acts as a kind of algebraic differential, encoding infinitesimal variations across the bundle in a way that is strictly governed by the polynomial nature of the variety itself. The entire construction is algebraic, built from the ground up without any reference to loops or continuous paths. Simpson's conjecture proposed that for any smooth complex projective variety, there exists a perfect correspondence between stable Higgs bundles with vanishing Chern classes and irreducible representations of the algebraic fundamental group. It was a statement of breathtaking scope, forging a bridge between the continuous and the discrete, the analytic and the algebraic. Proving it would mean that the deepest topological secrets of a variety were in fact already written into its algebraic DNA. The conjecture's elegance was matched only by its difficulty. For nearly 2 decades, it stood as a monumental challenge, a holy grail at the confluence of algebraic geometry, differential geometry, and representation theory. Progress was piecemeal, with special cases yielding to specific, often non-generalizable, arguments. A direct assault on the full problem seemed to require a new conceptual framework, a perspective that could somehow mediate between the 2 disparate sides of the proposed equivalence. Hélène Esnault, in a series of groundbreaking papers, many with her collaborator Michael Groschenig, furnished exactly this new perspective. Her approach was characterized by a brilliant and audacious strategy. She would solve the problem by moving it to an entirely different mathematical universe. Instead of wrestling with the conjecture in its native habitat of the complex numbers, a field of characteristic zero, she developed methods to transport the entire question into the world of positive characteristic arithmetic, the world of integers modulo a prime number p. This change of scenery was the masterstroke. While the geometry over the complex numbers is often more intuitive, the arithmetic of positive characteristic fields offers unique and powerful tools unavailable elsewhere, particularly those forged in the fires of p-adic Hodge theory. The arithmetic in these worlds is different. For instance, adding a number p to itself, p times results in 0, a behavior with strange and profound geometric consequences. Esnault's insight was that certain difficult analytic problems in characteristic 0 could become more tractable, algebraic problems in characteristic p. To operationalize this strategy, she and her collaborators developed a sophisticated technical apparatus centered on the notion of rigid local systems. A local system, which is the geometric object corresponding to a representation of the fundamental group, is termed rigid if it admits no non-trivial deformations. It is, in a sense, structurally locked in place. Rigidity is a strong condition, and Esnault theorized that for these special systems, the correspondence with Higgs bundles might be more readily established. The argument that followed is a testament to the profound unity of modern mathematics. Starting with a rigid representation of the fundamental group over the complex numbers, Esnault's method first involves finding an integral model of the entire setup, allowing it to be defined over a ring of numbers that can be meaningfully reduced modulo a prime p. Once transported into this positive characteristic world, the problem changes its character. Here, Esnault could bring to bear the full force of p-adic Hodge theory and newly developed tools related to the p-curvature of a connection. She demonstrated that in this setting, the rigidity of the representation forces its corresponding Higgs bundle to have a very specific constrained structure, which could then be shown to exist. The final, and perhaps most delicate, step was to lift this result back up. Using highly advanced theorems on the deformation theory of mathematical objects, she showed that the existence of this correspondence in the simplified world of characteristic p implied its existence back in the original complex world. This intricate triangulation, from characteristic 0 down to characteristic p and back up again, provided the first proof of a major part of Simpson's conjecture for rigid representations. The impact of this work resonates throughout contemporary geometry. The successful proof of this significant case of Simpson's conjecture revitalized the entire field, providing both a new template for attacking the remaining open questions and powerful evidence for the conjecture's truth. The techniques developed by Esnault and her collaborators, particularly the art of moving problems between different characteristics, have become a central paradigm in arithmetic geometry. Her work provides a key pillar for the geometric Langlands program, a vast web of conjectures that seeks to connect the geometry of algebraic curves to the representation theory of algebraic groups, itself a geometric analog of the original Langlands program. that links number theory and analysis. The bridge she built was not merely between Higgs bundles and fundamental groups. It was a bridge between entire fields of mathematical thought. These deep explorations into the fundamental topological and geometric structure of varieties, revealing their innermost symmetries, would themselves become the essential foundation for tackling some of the oldest and most concrete problems in mathematics. The search for integer solutions to polynomial equations. The search for whole number solutions to polynomial equations represents one of the oldest and most elemental quests in mathematics. These problems, named Diophantine equations, after the Hellenistic mathematician Diophantus of Alexandria, possess a deceptive simplicity in their statement and a profound difficulty in their resolution. For millennia, they were approached through a brilliant but often ad hoc collection of algebraic manipulations. The 20th century, however, witnessed a revolutionary transformation in perspective. The set of solutions to such an equation came to be viewed not as a mere collection of numbers, but as a geometric object, an algebraic variety, whose shape, topology, and intrinsic structure held the keys to its arithmetic properties. The abstract machinery developed to understand the geometry of these varieties, which Hélène Esnault had so masterfully refined, was now poised to be deployed against these most ancient and concrete of numerical questions. The central challenge in this domain, a direct descendant of Hilbert's 10th problem, concerns the distribution of integral or rational points on these geometric landscapes. For a given variety, does it contain infinitely many such points, or only a finite number? Answering this question is exceptionally difficult. A landmark achievement of the late 20th century was Gerd Faltings's 1983 proof of the Mordell conjecture, which established that an algebraic curve defined over the rational numbers with a geometric complexity measured by a genus greater than 1 can only have a finite number of rational points. This was a stunning confirmation of the principle that geometric complexity can dictate arithmetic scarcity. Falting's theorem settled the question for curves, the one-dimensional case. The great frontier then became the higher-dimensional analogues. What could be said about integral and rational points on algebraic surfaces, three-folds and beyond? It is here that Esnault's work, particularly her long and fruitful collaboration with Eckhart Vierweg, made a decisive impact. They brought the full force of higher-dimensional algebraic geometry to bear on the problem of integral points on surfaces and other varieties. Their approach was a powerful extension of the philosophy underlying Falting's work. They sought to identify subtle geometric invariants of a variety that could act as regulators, constraining the arithmetic behavior of its points. The core insight animating their research was that a variety that is sufficiently hyperbolic or curved in a properly defined geometric sense should be inhospitable to dense sets of integral or rational points. The task was to find the right mathematical language to quantify this notion of geometric complexity and connect it rigorously to arithmetic finiticness. The tools for this task came from the deep theories Esnault had helped to build. The theory of logarithmic geometry, for instance, became essential. In this context, logarithmic refers to a way of handling varieties that have well-behaved boundaries or singularities, which is precisely the situation one encounters when studying integral points. An integral point on a variety defined over the rational numbers can be thought of as a point that avoids certain places at infinity. The technical framework for analyzing this is a variety together with a divisor at infinity, a boundary that the integral points are forbidden to touch. The logarithmic structures developed by Fontaine, Ilusi, and Cato, and expertly wielded by Esnault and Vierweg, provided the perfect language for studying the geometry of these punctured spaces. Their work produced new and powerful proofs for the finiticness of integral points on certain algebraic surfaces. The innovation lay in the geometric criteria they established. They demonstrated that if a surface possesses certain properties related to its sheaf of differential forms, specifically, if its logarithmic cotangent bundle is ample, a technical term signifying a strong form of geometric positivity or curvature, then it can have only a finite number of integral points. They translated a statement about the positivity of a geometric object into a concrete statement about the sparseness of integer solutions. This was accomplished by relating these geometric conditions to deep inequalities involving characteristic classes, such as logarithmic Chern classes, which are numerical invariants that capture the topological complexity of the variety. The logic, while technically formidable, is conceptually beautiful. One can imagine that the geometric richness of the surface, as measured by these sophisticated invariants, imposes such strong constraints on any map from a simpler object into it, that only a finite number of such arithmetic embeddings are possible. The intricate internal geometry of the variety effectively repels all but a few integral points. This line of reasoning provided a robust program for extending the geometric approach to Diophantine problems into higher dimensions, offering a unified explanation for phenomena that had previously been observed only in specific cases. It supplied a profound rationale for why equations like x to the power of n plus y to the power of n equals z to the power of n have no non-trivial integer solutions for large n, a problem famously resolved by Andrew Wiles. The geometry of the associated Fermat surface is simply too complex to host them. Esnault's contributions to arithmetic geometry thus exemplify a defining feature of modern mathematics, the fruitful migration of abstract ideas into concrete applications. The highly theoretical world of vanishing theorems, fundamental groups and p-adic Hodge theory, which can seem entirely self-referential to an outside observer, proved to be precisely the lens needed to gain new clarity on the distribution of whole numbers. Her work demonstrated that the path to solving ancient arithmetic puzzles often leads through the most abstract geometric landscapes imaginable. This profound unification of geometry and number theory did more than just solve problems. It reshaped the very questions mathematicians thought to ask. The focus became a search for the fundamental geometric principles that govern arithmetic, a quest to understand the dictionary that translates between the language of shape and the language of number. In building and interpreting this dictionary, Esnault established herself as one of its most eloquent authors, and in doing so she cultivated a thriving intellectual ecosystem dedicated to its further study. The institutional embodiment of this intellectual ecosystem found its most prominent form in Berlin. In 2012, Hélène Esnault was appointed as the inaugural Einstein Professor at the Freie Universität Berlin, a position created to attract world-leading researchers to the city. This was a recognition of her stature and a powerful instrument for her to amplify her influence. The research group she established in algebraic geometry and number theory swiftly became a global center of gravity, drawing postdoctoral researchers and doctoral students from every continent. The atmosphere she cultivated was one of intense intellectual curiosity, characterized by a demanding standard of rigor and a collaborative spirit. Seminars were not merely presentations of settled results. They were active, often challenging, explorations of the frontiers of the field. Esnault's leadership style was one of deep engagement, pushing her students and colleagues to refine their questions, to clarify their assumptions, and to seek the most general and powerful formulation of an idea. Her influence as a mentor is a crucial dimension of her legacy, one written in the careers of the dozens of mathematicians who completed their doctorates under her supervision. She guided her students through the formidable technical landscapes of modern geometry, instilling in them her own distinctive taste for problems that lie at the nexus of different mathematical disciplines. To be her student was to be apprenticed in a particular mode of thought, one that sees a connection between a differential equation on a complex manifold and a question about rational points on a curve defined over the rationals. It was an education in seeing the hidden unity of the mathematical world. Her collaborations, numbering in the hundreds with a vast array of co-authors, paint a similar picture. Her work with Eckhart Viehweg stands as a monumental pillar of modern algebraic geometry, yet her intellectual partnerships extended across generations and specialties, reflecting a mind constantly seeking new perspectives and new problems. This vast network of co-authorship is a testament to a career built on dialogue, a career that viewed mathematics as a fundamentally social and cumulative enterprise. Viewing Hélène Esnault's body of work from a distance, one sees the emergence of a grand, cohesive intellectual program. Its individual theorems and papers, each a formidable achievement, serve as chapters in a single overarching narrative about the fundamental structures that govern mathematical reality. Her lifelong pursuit can be understood as a quest for the essential invariants of algebraic varieties. These are the core properties, encoded in concepts like cohomology, fundamental groups, and the intricate dance of connections and their monodromy, that remain unchanged as the variety itself undergoes continuous transformation. Her work consistently demonstrates that these abstract fingerprints contain profound, often surprising, information about the variety's most concrete arithmetic and geometric properties. The early work on vanishing theorems with Vieweg provided foundational tools, establishing which cohomology groups must be zero under certain geometric conditions. This was an essential act of clearing the ground, of understanding the constraints on the possible shapes and forms of algebraic varieties. Her subsequent explorations of the fundamental group took this inquiry to a new level of sophistication. The fundamental group captures the essence of loops and paths within a space, and Esnault showed how its representations, its mappings into groups of matrices, held the key to understanding systems of differential equations or local systems defined on the variety. This line of inquiry revealed that the topology of a space dictates the behavior of analysis upon it. The journey into p-adic Hodge theory represents the most ambitious expansion of this program. Here, the challenge was to build a bridge between two seemingly irreconcilable worlds: the continuous analytic world of complex geometry and the discrete arithmetic world of p-adic numbers. Her proof of the p-adic Simpson correspondence with Matthew Morrow and Moritz Kurz was a crowning achievement. It established a dictionary for translating between p-adic local systems and a new kind of algebraic object called a Higgs bundle, mirroring the known correspondence in the complex setting. This was a profound statement of unity, suggesting that the fundamental principles of geometry are so deep that they persist even when the underlying number system is radically altered. It showed that the invariants she had studied for decades were not artifacts of one particular domain, but were expressions of a more universal mathematical logic. Ultimately, her work offers a powerful and elegant answer to one of the deepest questions in mathematics. Why should the study of abstract shapes have anything to say about the properties of whole numbers? Esnault's career provides a compelling demonstration that geometry is the natural language for understanding arithmetic. The distribution of rational solutions to a Diophantine equation, a problem rooted in ancient number theory, can be understood by studying the topology of an associated geometric object. The intricate patterns of prime numbers find their reflection in the structure of p-adic cohomology. Her work transforms the relationship between these fields into a partnership of equals, where insights from one illuminate the deepest mysteries of the other. Her legacy, therefore, is a particular way of seeing. It is a perspective that finds the universal in the particular, the simple in the complex, and the arithmetic in the geometric. Through her theorems, her collaborations, and her mentorship, Hélène Esnault has sculpted the landscape of modern mathematics, revealing the profound and beautiful interconnectedness that lies at its very heart. Her work is a testament to the idea that the most abstract inquiries into the nature of form and structure can yield the most concrete truths, affirming that the pursuit of pure mathematics is one of humanity's most powerful tools for understanding the logical architecture of the universe.